All right, y'all. Here it is, lesson 10.2. Um, all about basically three laws that have to do with gases that relate pressure and volume and temperature. Uh, so here we go. Let's work through them. The first one we want to talk about is Boyle's law. Um, Boyle's law basically says if temperature and amount of gas in a container are held constant, so temperature doesn't change, the pressure of a gas is inversely proportional to the volume. Proportional. Sorry, I write too big. Anyway, so pressure inversely proportional to volume, which means when one goes up, the other goes down. Volume goes up, pressure goes down. Pressure goes up, volume goes down. Um, so as the volume shrinks in a container, you see here the volume shrinks. Particles collide with the container walls more often because they're closer, increasing the pressure. So the pressure increases. Okay, so volume decreases, pressure increases. I kind of like to think of it, I'll give you my example. Think of the classroom, right? So we're in the classroom, especially right now, there's not as many of us in the classroom, right? So the pressure's not that great. We're all spread out. There's a big space. We're spread out, not that much pressure. Imagine if we decreased the volume to the size of a Volkswagen, like a teeny tiny car, and then tried to put 8 people in that teeny tiny car, right? The volume decreased, so the pressure goes up. We're all squishy and squished together, and you're feeling that pressure, right? Because the volume has decreased. You increase the volume, like let us all out of the vehicle to stand in the parking lot, increase the volume, pressure decreases. There is no stress, there is no pressure. We are just out and about free. No one's touching us, no one's pushing against us. Low pressure, right? So pressure increases when volume decreases. Um, so another way to look at this equation, pressure, I don't really like this way, but it's this, a formal way. P is pressure, V is volume, K is a constant. We'll talk about that more later. The usable way to write this equation is right here. Okay? So we've got initial pressure, initial volume equals final pressure times final volume. So, but remember, as long as the temperature and the amount remain the same, temperature cannot change. And frequently, when you see problems like this, you'll see it say temperature doesn't change, right? At constant temperature, right? That way you'll know. All right. So this is the formula that we're going to use for Boyle's law. Let's do an example. Here we have the scientist has 2 containers. Container A is empty, has a volume of 25 milliliters. Container B contains a gas at a pressure of 1.5 atmospheres and has a volume of 25 milliliters. Okay. The scientist connects the 2 containers using a 5 milliliter tube. What is the pressure throughout this new system? Because we know the gas is going to go through that, flow through that tube and now be spread out, right? Gas always expands as much as it can. Okay? So first we had it trapped in here. Now we've expanded it to this whole area. Okay? So when we do these problems, first thing I always like to do, I like to write down as many numbers as I know. Okay? So initial conditions. The initial conditions, the volume was 25 milliliters. And the initial pressure was 1.5 atmospheres. At the end, the volume now is this whole thing. So this is 25, and this is 25. That's 50. But remember, it told us the tube was also 5 milliliters. So we have 25 plus 5 is 30, plus 25 is 55. So the whole entire volume here at the end is 55 milliliters. And the pressure, don't know. That's what we're trying to find. What is the pressure? Right? So that's where we're headed. So let's plug everything into our equation. Pressure 1, 1.5. Volume 1, 25. Equals pressure 2. I'm going to call it X because I don't know. And because I don't like writing question marks in my math equations. They mess me up. Volume 2, 55. Right? Here we just have simple algebra problem. Right? Simple math now. Multiply here, we get 37.5. 37.5 equals 55x. Divide by 55. And we get x, or my new pressure, is equal to 0.682 atmospheres. New pressure, 0.682. With these, it's always really good to check. It's easy too, right? Remember we said volume increases, pressure decreases. So here in this system, my volume definitely increased, right? Went from 25 to 55. My pressure decreased from 1.5 to 0.6. So that's just a quick little check I could do. Make sure I got the right answer. Volume increased, pressure decreased, good to go. Okay, so that's Boyle's law. One increases, the other decreases. Next law. Lovely French scientist by the name of Gay-Lussac. He compared pressure and temperature. So again, some things remain constant, right? This time the amount is constant and the volume is constant. Okay. So the pressure of a gas is directly proportional to the temperature. That means one goes up, the other goes up. Temperature goes up, pressure goes up. Pressure goes up, temperature goes up. Temperature goes down, pressure goes down. Okay, they're directly related to each other. So, as you can see here in my little example box, as the temperature increases, temperature goes up, particles have more kinetic energy, so they're moving faster. They collide with the container walls more often, which increases the pressure. Okay, so temperature increases, pressure increases. All right, so the formal way to write that, we'll just label all these. We know P is pressure, K is the constant. I promise we'll talk about that later. T is the temperature. Okay, sorry, hit the camera with my pencil. Okay, but here's the usable equation. Pressure divided by temperature equals pressure divided by temperature. But remember, the amount, can't spell, amount, and the volume remain constant. It's very important that the amount and the volume remain constant in order for this to work. Okay? All right. So here's what our problem says. Scientist measures the pressure of a particular gas in a closed fixed volume, remember, fixed volume container, is 1.25 atmospheres. The temperature is 20 degrees Celsius. Scientist heats the container to 75 degrees Celsius. Right? So he's heating up the container to 75. See his little flame under there? It's kind of old-fashioned, but it's there. What is the new pressure of the system? Now, the first thing we need to do, Super important to remember. All of these gas laws, like remember I said in the last lesson, deal with temperature in Kelvin. We are not going to go that detailed. Okay. So if the problem gives you a temperature in Celsius, you must convert it to Kelvin. Okay. You must. It won't work if you don't. I guarantee you will get the wrong answer. Please just add 273 to it all the time. Super important. All right, let's figure out what we got here. So the initial pressure was 1.25 atmospheres. The initial temperature was 20 degrees Celsius. Okay, scientists, final temperature, final pressure, we don't know. What is the new pressure? That's what we're trying to find out. Final temperature was 75 degrees Celsius. Okay, first thing we need to do, add 273 to both of these. So we get our proper temperature, which that is 293 Kelvin. This one is 8, 7, 7 is 14, 348 Kelvin. All right, now I can plug into my equation. Pressure 1, 1.25 divided by 293 equals X. Pressure 2 we don't know, divided by 348. Then all we have to do is some lovely little cross multiplying, right? Super easy. Super easy. We get 1.25 times 348 is 435. 435 equals 293x. Divide by 293, divide by 293, and x equals 1.48. 1.48 atmospheres. And just like before, we can check. Temperature went up, pressure went up. 1.25 to 1.48. So with temperature and pressure, they do the same thing. Temperature goes up, pressure goes up. Okay, so that's that law. Temperature up, pressure up. The last law is Charles's law, and it relates volume and temperature. So we got volume and pressure with the first one. We got pressure and temperature with the second one. And now we have volume and temperature. Okay, so again, just like before, if the amount of gas and this time the pressure stay constant, the volume and the temperature are in direct proportion. Which means when the volume goes up, the temperature goes up, and vice versa. Okay, so volume up, temperature up. Just like it says here, as the temperature increases in a container that can expand to provide constant pressure, the volume will increase. So as long as the pressure remains constant, the volume is going to increase. Okay, here's that formal equation. Volume, constant, temperature. But here's our usable equation. Volume divided by temperature equals volume divided by temperature. Remember, as long as the pressure and amount remain constant. We'll get to one where they don't remain constant in the next lesson. All right, so here's my problem. Scientist has a balloon, 22 degrees Celsius, with a volume of 1.2 liters. He heats up the balloon to 40 degrees Celsius. What is the new volume of the balloon? What does the volume of a balloon do if you heat it up? Reminder, we've got to convert that temperature to Kelvin. Super important. Okay? All right, let's solve our problem. So initial volume, 1.2 liters. Initial temperature, 22 degrees Celsius. Final volume, don't know. That's what we're trying to find. What will be the new volume? Final temperature, 40 degrees Celsius. So first, take both these temperatures, add 273. That makes that 313. And this one, 5. All right, so this one's 295. Okay, let's plug everything in. 1.2 divided by 295 equals x divided by 313. And again, I'm going to cross multiply. So 1.2 times 313 is 375.6. So we get 375.6 equals 295x. Divide by 295. Sorry for the squishiness here. And I get x is equal to 1.27 liters. Let's double check. The temperature went up, which means the volume should go up, which it did just a little bit. Temperature up, volume up, and we're good to go. So that's the law, Charles's law, that relates volume and temperature. If you want to try an example of Charles's law when you're done with your balloon in the lab that you're doing, if you want to blow it up, tie it off, and throw it in the freezer, it should shrink. Temperature down, volume down. Try it if you want. So the volume of your balloon should shrink. Just kind of a fun thing to do.